Less than 24 hours after the discovery was announced, a radio telescope in Northern California turned to face an object that had just arrived from another star system and began to listen. Over the following months, that telescope would sift through 74 million individual signals, narrow them down again and again, chase 11 of them that briefly looked like something more than noise, and arrive, finally, at an answer. Not the answer half the internet was hoping for, the answer science actually found. And that gap between what people wanted to hear and what the data actually said is the real story here, and it says more about us than it does about the object itself. This is the story of what happened when the SETI Institute pointed the Allen Telescope Array at 3I Atlas, the third confirmed visitor from beyond our solar system, and asked the only question that has ever really mattered about objects like this one. Is anybody home? To understand why anyone would even ask that question about a comet, you have to go back to the beginning of this object's story, because 3I Atlas did not arrive quietly. It was first spotted on the 1st of July last year by the Atlas Survey, the Asteroid Terrestrial Impact Last Alert System, a network of telescopes built specifically to catch anything moving through our solar system with dangerous intent. And what it caught instead was something moving with impossible origin. The object's path was hyperbolic, open at both ends, far too fast to be captured by the sun's gravity. It had not formed here. It was not going to stay. It was the third confirmed interstellar object ever documented, following a strange little visitor called Oumuamua in 2017 and a genuine comet named Borisov in 2019. And almost immediately, 3II Atlas proved to be the biggest, brightest, and fastest of the three. Within weeks, the object had already earned a reputation for behaving strangely. Its trajectory was unusually eccentric even by interstellar standards. Its outgassing, the visible plume of gas and dust released as sunlight warmed its icy surface, was enormous, tens of millions of tons of water. Vapor released in the span of weeks around its closest approach to the sun. And despite producing that much material, it showed remarkably little of the trajectory-nudging thrust that level of activity should normally cause, suggesting either an unusually massive nucleus or something about its behavior that did not fit the standard comet playbook cleanly. Later, another team of astronomers would notice a strange forward-pointing glow in its coma and propose, cautiously, that it might not be dust at all, but something closer to a loose cluster of solid fragments traveling alongside the object. None of that, on its own, proves anything exotic. Strange trajectories and unusual outgassing happen in nature, but interstellar objects are rare enough and strange enough that when one shows up, the scientists who take the search for extraterrestrial intelligence seriously do not wait around for permission to check. If there is ever going to be a moment when humanity detects a genuine signal from beyond our solar system, an object that arrived from another star, passing directly through our neighborhood at close range, is about as good a candidate as physics is ever likely to hand us. So the SETI Institute did what its name promises. It listened. The instrument they used is called the Allen Telescope Array, a forest of 42 linked radio dishes standing in a high desert valley at the Hat Creek Radio Observatory in Northern California. It is built for exactly this kind of rapid response, a system designed to swing toward a newly discovered object of interest and begin gathering data before the opportunity closes. In the case of 3I Atlas, that response began remarkably fast. Observations started roughly 23 hours after the object's discovery was first announced to the world, an almost unheard of turnaround in a field where most targets take weeks or months to schedule. Over 5 separate observing sessions, the array logged more than 7 hours pointed directly at 3I Atlas, sweeping across an enormous stretch of the radio spectrum, from 1,000 all the way up past 9,000 megahertz, a range chosen because it comfortably covers the frequencies most associated with artificial engineered transmissions, rather than the broad, smeared emissions nature tends to produce on its own. Specifically, the team was hunting for what radio astronomers call narrow-band signals, tight, focused spikes of energy concentrated in an extremely narrow slice of frequency, the radio equivalent of a laser beam rather than a floodlight. Stars, planets, and comets do not naturally produce signals like that. Radio transmitters do. And in that first raw sweep of data, the results looked, for a moment, almost overwhelming. The array flagged something in the neighborhood of 74 million individual candidate signals across the observing sessions, a number that sounds, on its face, like the biggest technosignature detection in human history. It is also, to anyone who has worked in this field for more than a week, a completely expected number, and not remotely the sound of an alien transmitter. It is the sound of Earth. Because here is the part of the story that rarely survives the trip into a dramatic headline. This planet is extraordinarily loud in a radio sense and has been for the better part of a century. cell towers, satellites, television broadcasts, garage door openers, air traffic radar, half-broken electronics in laboratories a few miles from the telescope itself. Nearly every one of those 74 million candidate blips traced back not to 3i Atlas 90 million miles away, but to human technology operating right here, contaminating the data the same way stray light contaminates a long-exposure photograph. Radio astronomers have an entire toolkit built around identifying and stripping this interference out, and the SETI team applied it methodically, pass after pass, filtering candidates that also appeared when the telescope was deliberately pointed slightly away from the object. A technique that reliably separates genuine cosmic sources from local earthly noise, because a real signal from 3i Atlas would only show up when the dish was actually aimed at it. That filtering process cut the field down hard. 74 million candidates became roughly 200 that survived the automated cuts. 200 became 211 plots pulled for direct human review, researchers physically examining the frequency and drift rate signature of each one. Of those, 11 stood out at first glance, appearing measurably brighter in the beam pointed at the object than in the reference beam pointed away. From it, briefly, tantalizingly, the kind of signature that makes a research team sit up a little straighter. None of them held up. Some of the 11 turned out to be broader, modulated signals rather than the clean, narrowband spikes the search was specifically designed to catch, a shape more consistent with ordinary radio frequency, interference bleeding unevenly across the band than with an engineered artificial transmission. Others matched, once cross-checked, known terrestrial communication frequencies already logged and cataloged from prior surveys at the same site. One by one, every candidate that had briefly looked interesting was traced back to a mundane, thoroughly earthbound explanation. By the time the analysis was complete and published in the Astronomical Journal in June of this year, the conclusion was unambiguous. No credible narrowband radio technosignature was detected from 3i Atlas. Nothing. Not even close. But, and this is the detail that turns a negative result into a genuinely useful transmission of its own, a well-designed search that finds nothing still tells you something concrete. And the SETI team was careful to quantify exactly what. Based on the sensitivity of the array and the object's distance from Earth at the time of observation, roughly 3 1/3 astronomical units, the researchers calculated the maximum power any hidden radio transmitter on or near 3i Atlas could have been operating at without being detected. That ceiling works out to somewhere between 10 and 110 watts, depending on the exact frequency involved. For context, roughly the output of a household appliance. Anything broadcasting above that threshold in the frequencies scanned would not have escaped notice. So, while the search cannot prove the absolute absence of any transmitter whatsoever, it can say with real confidence that nothing louder than a microwave oven was quietly humming away on that object as it crossed our solar system. That is, in its own way, the actual transmission this story is named for. Not a message beamed back from an alien probe, but a precise, quantified, scientifically rigorous confirmation sent not by 3i Atlas, but about it, a hard upper limit on what could possibly be there, delivered by 7 hours of careful listening and months of methodical filtering. And it confirms in plain terms exactly what the rest of the astronomical evidence had already been suggesting for months. This object behaves like a comet, looks like a comet, sheds gas, and dust like a comet, and now, on top of all of that, stays silent like a comet. Every independent line of investigation keeps arriving at the same unglamorous, thoroughly natural conclusion. Why then does the headline, "No alien signal was found," feel to a certain corner of the internet like the answer nobody wanted to hear? Because for a few months, 3i Atlas had become something bigger than a comet in the public imagination. A prominent Harvard astrophysicist had already floated the idea, publicly and repeatedly, that the object's unusual size, its oddly restrained response to its own outgassing, and later that strange forward-facing glow in its coma might be consistent with something engineered rather than grown. A possibility he was careful to frame as one hypothesis among several, but one that traveled far, faster and further than his careful qualifiers ever did. By the time the SETI results were published, a real appetite had built for a very different kind of headline than the one the data actually supported. That is not a failure of the science. If anything, it is the process working exactly as intended. A serious hypothesis was raised. A serious independent test was designed specifically to check it. The test was run rigorously, its results were quantified honestly, and it came back negative. In any other context, that sequence is simply called doing science correctly. It only reads as disappointing if the goal, quietly, was never really to find the truth, but to find a particular kind of story. There is also something worth sitting with in the researchers' own explanation for why they bothered at all. given how unlikely a positive result always was. One of the study's authors put it plainly: understanding what a natural interstellar object's radio signature looks like in detail is the necessary baseline for ever recognizing a genuinely artificial one if it ever does show up. You cannot identify an anomaly without first knowing with real precision what normal looks like. Every interstellar visitor that gets this kind of careful negative result scrutiny makes the eventual detection of something truly unusual, if that day ever comes, more credible, not less. Voyager, that same researcher pointed out, is itself technically an interstellar object now, quietly leaving our solar system the way 3I Atlas entered it, and it too will one day be a faint artificial radio source drifting past some other star system's equivalent of an Allen telescope array. Understanding the natural background is what will let some future civilization, or some future version of us, actually recognize technology when it finally does show up in the data. So the transmission, in the end, was real. It simply was not the one the title promised, and it did not come from 3I Atlas at all. It came from a valley in Northern California, 42 dishes deep, carrying a message built out of 7 hours of careful listening, 211 examined signals, and 11 false alarms chased down and ruled out one at a time. The object is exactly what nearly every other line of evidence already said it was: a comet. Old, massive, strange in a few genuinely unexplained ways, but natural through and utterly, measurably silent. 3I Atlas continues on its way now, already too far from Earth for most instruments to study in meaningful detail, heading Tau, or to close pass by Jupiter, before it leaves our solar system permanently and returns to the interstellar dark it came from. It will never send another transmission because it never sent one in the first place. But the search built to check that fact left behind something more durable than a single headline, a hard number, published and peer-reviewed, standing as a quiet correction to every version of this story that got there first. Sometimes the most important discovery a telescope can make is confirming, carefully and completely, that there was nothing there to find. It is worth taking a moment to understand exactly how a search like this manages to be so confident in a negative result, because "we didn't find anything" can sound, on the surface, like a shrug rather than a scientific conclusion. It is not. Every step of the process the SETI team followed was designed specifically to convert a vague absence into a precise, defensible claim. Start with the sheer scale of the raw data. 74 million candidate signals is not a small number to sort through by hand, and no team of astronomers actually could. Instead, the process leans on layers of automated filtering, each one built to exploit a specific, reliable difference between a genuine cosmic signal and terrestrial noise. The first and most powerful of those filters is the dual beam technique itself, pointing one beam of the array directly at the target, while a second beam, only slightly offset, watches a patch of empty sky nearby. A real signal originating from 3I Atlas, 90 million miles away, would only appear in the beam actually, tracking the object. A signal caused by a cell tower, a satellite, or a piece of malfunctioning lab equipment a few miles from the observatory does not care which way the dish is pointed. It shows up in both beams equally, or nearly so, because its source has nothing to do with the sky at all. That single comparison alone eliminates the overwhelming majority of false candidates in one pass, which is how 74 million shrinks down to a number in the low millions almost immediately. From there, the remaining candidates get checked against known interference catalogs, running lists built up over years of operating the array at that same physical site, of specific frequencies known to be contaminated by cell networks, GPS satellites, aircraft radar, and dozens of other everyday technologies that happen to broadcast in bands radio astronomers also care about. Any candidate signal that lines up with an already documented interference frequency gets flagged and set aside, not because it is proven uninteresting, but because it matches a known, mundane source closely enough that treating it as a mystery would be scientifically dishonest. What survives after both of those filters is a genuinely small, genuinely puzzling handful of signals. In this case, a little over 200, worth a human being actually, sitting down and looking at the data directly, frequency plot by frequency plot, checking each one for the specific visual signature real narrowband techno-signatures are expected to have. A tight, consistent line, rather than a smeared or wandering one, present in the target beam and essentially absent from the reference beam, with a drift rate consistent with what you would expect from an object moving the way 3I Atlas was actually moving relative to Earth at the time. That drift rate check turns out to be one of the more elegant parts of the whole method, because 3I Atlas was moving through space along a well-known, precisely measured trajectory. Any genuine signal originating from the object itself should show a very specific, predictable shift in frequency over the course of the observation, the radio equivalent of the Doppler shift that changes the pitch of a passing ambulance siren. A signal that does not drift the way the math says it should is not coming from 3i Atlas, no matter how clean or narrowband it otherwise looks. This is the level of scrutiny that took 211 surviving candidates down to 11 worth a second, a harder look, and then took those 11 down to 0. It is a slow, unglamorous, almost bureaucratic process, and that is precisely what makes the final result trustworthy rather than merely convenient. Nobody involved in this search wanted a boring answer. A confirmed technosignature from an interstellar object would arguably be the single biggest scientific discovery in human history, and every researcher on that team would have been thrilled to find one. The fact that the process was built to be this rigorous, this resistant to wishful thinking, and still came back empty, is exactly why the result carries weight instead of simply reflecting what the researchers expected to find going in. And that, ultimately, is the part of this story worth carrying forward long after 3i Atlas itself has faded past the reach of our telescopes. The instinct to hope for something extraordinary is not the problem. It is, in many ways, the same instinct that built the Allen telescope array in the first place, that funds SETI research at all, that sent 7 hours of precious observing time toward a single icy visitor on the off chance IT might be something more. The problem only begins when that hope gets treated as evidence, when a headline promises a confirmation the data never actually delivered. The real discipline of science was never in refusing to hope. It was in being willing, every single time, to let the listening decide the answer instead of the wanting.